So, I'm a big believer in terms of chemistry. I've already said this before. I like doing a lot of hands-on stuff. Because of that, the way the textbook goes in order of, I don't go in order of the textbook. The reason why I don't do that is that the first unit listed in your textbook, there's really not a lot of experiments that you can do, which kind of sucks in my opinion, because I want to just hop right in and actually have you guys do stuff. So we're actually going to start with the third unit in your textbook. So in case you're wondering, I am kind of hopping around a bit, but I promise I do have reasons for it. The biggest reason is so that we can actually do some hands-on stuff. So we're going to start off with a unit on solutions, acids, and bases. So let's just talk a bit about solutions. Do you guys know the word solution? You've heard it before? Yeah. Okay, so I've got a definition here for you for a solution, a very science definition. Write it down if you can't memorize it. Don't forget, your guys' chemistry data book, you can write anything you want in there. There are like 8 pages that I'm sure you can find blank space in there. So in case you can't remember this definition, here's the definition of a solution. It is a homogeneous, or maybe you pronounce it homogeneous. I pronounce it homogeneous, but there's different ways of saying it. It's a homogeneous mixture composed of a solvent and a solute. You guys ever heard that definition before?
Yes.
Maybe. There's a lot of words in there I need you guys to know.
Solute is a solid.
Okay, that's close. It's actually not always true, but that's not a bad way of starting. A solute is usually something solid, and a solvent is usually something liquid. And you always put the solute inside the solvent. But that's not the official definition of solute and solvent. Before I get to that, though, I want to talk about the word homogeneous or homogeneous. Do you guys know that word? Homo or homo as like a prefix means the same. So it means like the same throughout. Meaning that when you look at it, you shouldn't be able to see anything different. I have 2 different solutions I made here that I'm going to reference over the next little while. I know you guys can't see this close up, but this is Kool-Aid crystals. And as you look at it, it's pretty uniform, if I use that word. It's homogeneous. I cannot see a difference in there. Like, it's all yellow. It's see-through. Do you guys know what the word for, like, see-through is? There's like a fancy word for it. Transparent's not bad. Translucent also works. Transparent also works, so I'll accept either. Transparent or translucent will work. Okay. This one right here, you guys probably can't see this quite as well, but I took some oil and I put oil on top of water. I don't know if you guys can see this from where you're at, but there is definitely like a layer sitting on top. Okay. And if I try to mix this stuff up, I'm going to stir it like really, 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 really good. This is not going to be a homogeneous mixture, because what's going to happen is I'm going to be able to visibly see the oil on top. I don't know if you guys... Can you can see like on the top there's like bubbles. I'll walk around, right? Like you can see the oil on top. Does that make sense? So, it's like you can see as I stir it up here. Hopefully you'll see in a second here. Like there's definitely like a layer on top there. So in the middle there, like there's all the oil chopped in the top there. Same thing here. Like this is visibly like a layer sitting on top. So, in terms of notes, by the way, I think I've mentioned this to a lot of you guys before, but I give you guys printed notes so that you can write down some of the stuff I say. So a really good thing maybe to write down, if you want to write something down, is what homogeneous means. So I might just say this is uniform, or the same throughout. So a solution, a proper solution, you should not be able to see layers to it. So in terms of these 2 guys right here, I would say the orange juice crystals, those are a solution. They dissolved, whereas the oil is not really making a solution per se. The other words I want to talk about are solute and solvent, and I think I have those definitions on the next slide. I do. Haley gave a definition earlier, which isn't bad, but it's not complete. A solvent is usually water. Usually. Oh my goodness, how do you spell usually? And a solute is usually a solid. Again, usually. But that's not like a hard and fast rule that says that you always have to dissolve a solid in a liquid. You can actually dissolve pretty much anything in anything. You can actually have solids in solids and liquids in liquids and gases in solids, and if that makes sense. So better terms to use here. A solvent is the medium the solute is dissolved in. Do you guys know what medium is? Stuff is a pretty good definition for it. Medium would be like the stuff. Okay. If I were to ask you what medium sound waves travel through,
Air.
You might say air. It's the stuff that sound waves travel through. If I were to ask you what medium did you go swimming in, you'd say you were swimming in water. So just a fancy science word. Okay. Here's some more words that I hope you guys recognize from some point in science. A pure substance has only one type of molecule. Do you guys know that term? A mixture then has two different kinds of molecules or more. And then heterogeneous or heterogeneous means there are different types that you can visibly see, whereas a homogeneous means you can't tell the difference. So, I got a flow chart that I found online that I hope makes sense here. An element is just one thing, like just pure gold, pure copper. Okay. A compound is still just one thing, but the thing is the only thing. I'm not saying this very well. The thing itself has like more than one element. Like say this could be water. You could have H2O, H2O, H2O. This could be CO2. So you can have more than one element, but all you have is that one item. Whereas then mixtures are where you have like some of each. I always like to think of Chex Mix as a good example of a mixture. You guys know what I mean by Chex Mix? Where like you have like the little Cheerios and the Shreddies and the pretzels and stuff. It's clearly a mixture because there's more than one thing involved. Does that make sense? Is it homogeneous or heterogeneous? Because you can clearly see differences there. Does that make sense? Whereas if you were drinking apple juice probably has a whole bunch of things dissolved inside of it, right? But can you actually see layers to apple juice? Probably not. What about orange juice? And then you start getting into questions of, well, it depends. If orange juice has a lot of pulp in it, well, now it's not a homogeneous mixture anymore, right? But if you filter out the pulp, now it's homogeneous. Does that make sense? Okay. Kind of back to the point that I made earlier when Haley suggested solids and liquids, you can actually have solutions between pretty much any two states of matter that you want. Let me give you some other examples. You can actually have a gas dissolved in a gas. Okay? Air is actually a mixture. Okay? Because you actually have oxygen dissolved in nitrogen. Actually, air is more than just oxygen. There's also like methane emissions, carbon dioxide. You know, you might have trace amounts of CFCs, if you know what those are. Okay. But really, you have small stuff dissolved in a larger something. Air, I believe, is about 78% nitrogen, give or take. So if oxygen is like, say, 23%, that's probably too low. Let's go 20%. Then the smaller amount is dissolved in the bigger amount. Okay. Water is actually a good example of a gas dissolved in a liquid. You can have like water bubbles inside of water sometimes. You ever notice these before? And so long as they're uniform throughout, that's a solution. Ice will actually have water bubbles caught inside of it, so you can even have a gas and a solid. Antifreeze is a good example of liquids and liquids. You can actually pour methanol in water and make antifreeze. Sugar in water, like syrup, that's a solid in a liquid. And you can even have solids in solids. They're called alloys. Do you guys know those terms? Yeah. An alloy is where you like melt two metals together. Steel's a good example.
Alloy with like iron and nickel.
Yeah, bronze is another one, where you have like, I think one is carbon and copper or something. So, okay, one thing I want you guys to know though, when we deal with solutions, we almost always deal with the solution that Haley mentioned, which is a solid in a liquid. And the liquid is almost always water.
Mr. Bonnet, can you please call 100? Mr. Bonnet,
Now,
please call 100.
because we're going to dissolve things in water, it's really important to notate that. And we've already started doing that. We use this little symbol right here, AQ. You guys remember what AQ stands for? Good, aqueous. I think that's Latin based for water, something like that, right? So aqueous means that this NH3, what is NH3? Ammonia. Ammonia. This means that your ammonia has been dissolved in water. Okay. Well, you can dissolve things in water, but does it have to be water? No. So sometimes we put other things in brackets, and this is pretty rare though. This would be iodine dissolved in good alcohol, yeah. Yeah. Now, one thought here. Alcohol in terms of chemistry is not drinking alcohol. There are lots of different types of alcohols. I have probably like 8 or 9 in the back of the lab, and you should not drink any of them because that's not what they're meant for. Yeah, that's not the same thing. Drinking alcohol is just like one specific kind of the larger group of alcohols. So. Okay, another term I need you guys to know is called an electrolyte. And maybe you've heard this term before if you're like an athlete and you're drinking Gatorade. Or I talk about this with my daughters when they get really sick. When Cami starts to throw up, she needs to have some more electrolytes in her system. You guys heard that term before? Gatorade is famous for electrolytes, but in science, electrolytes have maybe a bit of a different definition. Basically, electrolyte means that it can conduct electrical current. I have no idea why I spelled it with an A. Current. Current is like, with an A is like a BlackBerry current. Okay. If something is capable of conducting electricity, it's called an electrolyte. And I want to show you guys a quick test we have for whether it conducts electricity. This is a basic conductivity apparatus. And as I press the button, you see how it says on? Okay. If a full circuit is made, I don't know if this will do it. No. Apparently my body's not conducting electricity, but like the meter will start to go up because like a full loop will be made between the battery in here and both of these little, I don't know, probes, I guess. So, this is, I think it's probably meant for going in solutions. So if I put it inside this thing right here, did the bar go up? Yeah. Okay, good. This thing conducts electricity. Whereas this one right here, you can see, it's doing nothing, I'm hoping. All right, so first of all, this thing isn't really even a solution though because this thing didn't even dissolve anything. Like I can clearly see the layers to it. But long story short, anything that conducts electricity is called an electrolyte. Okay, electrolytes. There's 2 different kinds we have. We call them strong and weak electrolytes. I'm sure that kind of intuitively makes sense. If you're a strong electrolyte, you do a great job of conducting electricity. Whereas if you're a weak electrolyte, you do kind of a good job of conducting electricity, but you're not really great at all. The opposite of strong and weak would be a non-electrolyte, which doesn't conduct electricity whatsoever. Does that make sense? So you've got kind of a spectrum here. You've got no conducting electricity whatsoever, then you've got conducts a little bit, maybe like 1%, but that still counts. And then over here, strong means it conducts really well. Does that make sense? Okay, here's what I need you guys to know. All ionic compounds are considered electrolytes. So if I tell you that a compound is dissolved in water, it should conduct electricity. You guys remember what ionic means?
That's like non-metal.
Let's talk about that for a second here. Ionics are made of, usually we say a metal and a non-metal. But maybe a better way of calling them is they're made of cations and anions. What's the charge of a cation? Good. Cats have pos. Yeah, positive. Whereas anions are negative. Okay. Bit of a physics lesson here. What is electricity? Electricity is the motion of electrons through a circuit. Right? In my physics class earlier today, we talked about the idea that really you can't have positive charges move. Positives don't move, but negatives can move. Negatives are electrons, and negatives are capable of moving wherever you want them to. Static electricity is a good example. We need to get that little bit of a zap. Okay. Well, if electricity is the movement of electrons, those electrons need to be able to move through things. And if you have positive and negative charges, you have the ability for electrons to move through these. Does that make sense? Electrons can pass through positive and negatives. That makes sense. But covalent is a bit different. What are covalent compounds made from? Two nonmetals. Non-metal with another non-metal. And these guys function a little differently. They have to share their electrons. Because these electrons are shared, they are not available. And because the electrons are not available, electricity can't pass through these guys. So electrons can not pass through. So long story short, if something is ionic, ionics are made of positives and negatives. Good. If we have positives and negatives, electrons are actually able to flow because they'll flow away from the negatives and towards the positives. And so they can move their way through the circuit. Make sense? But if you have a covalent compound, which is only anions, which are both negative, the electrons won't be able to flow through. First of all, the electrons are actually shared in a bond, so they're not even available for moving whatsoever. Second of all, will electrons want to touch other electrons? Again, from my physics class this morning, for those of you guys in that class, electrons repel other electrons. So you can't make a circuit if all you have is negatives. You're going to need some positives and negatives. So, long story short, back up to the top here. All ionic compounds are electrolytes. Okay. There are a few, very, very few known molecular compounds that can conduct, but very few. Typically, molecular compounds don't conduct electricity.
What other compounds that do?
Here's a couple examples, and CHCl and NH3. Usually I have to give you the exceptions. Okay. So far so good?
Yeah.
Mostly today is a lot of theory. I have another term I want to describe for you. The term is called dissolving. You guys probably know the term dissolving. If I had Kool-Aid crystals and I poured the Kool-Aid in the water and I stir them up, you can probably imagine that they dissolve. You know that term, right? Well, it's possible actually to make Kool-Aid so thick. I just keep pouring more and more crystals in.
Saturation.
That's a word we're going to talk about eventually. Yeah, we call it saturated, where really, will I be able to stir those crystals in? I'd say probably not. In my family, Melissa's grandparents are actually very famous when they make juice. One of them is very chintzy with the juice crystals, and you're basically drinking like water that has like a little bit of juice crystals in it. And I believe that's grandpa. Whereas Melissa's grandma, when she makes a juice, she just like dumps it in, right? And so when you're drinking it, like it is so thick with crystals and sugar. You know what I mean? Well, yeah, you can taste the diabetes, the cholesterol in your heart. The term I want to use then, in terms of that, is called dissolving. What is happening at like a molecular level when something dissolves? Okay. I'm a big fan of analogies. This is one of my favorite ones. I hope this one's okay. Imagine that you are sodiums and chloriums. Imagine that we're going to try to dissolve you guys in an elementary school playground. And so we go over to wherever WA Day is, and like there are like what seems like 1,000 little kids just out on the field. The little kids are going to be the water molecules, and you guys are the NaCl particles. By the way, NaCl, ionic or covalent? Which means it can separate into positive and negative. Okay? Well, imagine that you guys are out on the playground at WA Day, and you're all kind of stuck together as a solid. But then they let out all the little kids, and the little kids just come ripping through you guys. Now, I know you guys are pretty big, and you can probably like take a couple of grade 5s. But like hypothetically, let's say that there were like thousands of them out there. What would happen to you guys? You would eventually get separated. You'd have to, right? Like those little rugrats there'd be so little room for you out on the playground that eventually you guys would get separated and pulled apart. And that's kind of what's happening here, is all of these little bitty water particles, there are so many of them that they will rip this apart.
Is that like what happens with like ozone? Cause like doesn't like chlorine break up ozone?
I think that's a little different. That's a chemical reaction other than dissolving.
Oh.
'Cause I think it actually like changes it to something different. So the analogy I like to imagine here then is these particles here, they are overrun. I hope that analogy makes sense. Like we're not talking like 100 fifth graders, we're talking like 1,000,000 fifth graders. I know you guys are pretty tough as high school kids, but you couldn't take 1,000,000 fifth graders. And so they are totally going to rip you apart if they wanted to. Does that make sense? Oh, that's the analogy I'm using. Okay. So, if you guys could stick together as one big group, you'd be a solid. Okay?
That's like my worst fear.
But what would happen is, imagine that you were all stuck together here. Eventually, all of these little fifth graders would come and pull this person away. And then they'd pull this person away. And I mean, if you were right in the middle, you might think, I'm nice and safe. Those fifth graders aren't going to get to me. But I mean, slowly over time, they would wear you down. Well, that's what happens when something dissolves. Yes.
So is that like sugar dissolved? Isn't it like C6H12 like those?
Good. Yeah, actually, sugar doesn't really dissolve properly because it's actually a molecular compound.
So like they don't mix up.
Yeah, they don't separate as effectively. They actually separate like a little bit, but not really. Okay. Does that make sense? Okay. One more thing. Normally, things are very stable in their positive, negativeness right here. Normally, things are not very stable when you rip them apart. But because all of these individual chlorines and sodiums are surrounded by a whole bunch of water molecules, which are really like little grade 5s, it actually makes them very stable.
Really?
Yeah. It adds to the stability.
That's why you drink salt water and not pepper.
Say that again?
If you like put like table salt in a cup of water, like when you like have.
Well, you can drink it. I believe salt water is a little different because it messes with some of the balance in your body because you shouldn't drink like ocean water. But that's more of a biology thing. That has more to do with Oh, okay.
Like when you bring it to help you to like.
Oh, yeah. Okay.
You guys are like, oh, you can't swallow it. I knew.
Anyways, back to this. The idea I want to go for here then is if you have like an ionic solid and you add it to water, what's going to happen is it's going to get ripped apart. So normally it's a nice solid, thick structure. You know, it's going to be fine. But if it can dissolve, the water will rip it apart into different little pieces. And so what you'll have is individual Na pluses and Cl minuses. Normally, sodium does not come in a plus form. But if it is surrounded by a whole bunch of pieces of water, then it can come in a plus form. Normally, chlorine does not come in a minus form.
I thought
But-
it always comes in a plus one.
Well, normally by itself, it comes as like chlorine gas. That makes sense? Normally it comes as chlorine gas, and normally it comes as sodium solid. Does that make sense? Yeah, normal things won't have any charge to it, which is kind of what we worked on a week and a half ago. The idea of, well, what will sodium come by itself? It'll come as sodium solid. Hydrogen would come as a gas. Mercury would come as a liquid. Does that make sense? But it is possible to make it a plus or a minus. But here's the one rule. The only reason it breaks into positives and negatives is because those billion grade 5 water molecules rip them apart. So we have to give them a little bit of credit. So afterwards we write the state of matter, AQ, which we've already worked with a bit in your data booklet. Now, some things are very easy to break apart. But there are some compounds that actually don't break apart all that well. So sometimes we actually leave them as solids, depending on how that table in our data book works. Okay. I've got another diagram here that hopefully helps explain what's happening when you dissolve. You've got this nice clump of grade 12 or grade 11s, I guess, all stuck together nicely, but they get overrun by water molecules, the grade 5s. I don't know. I like that analogy. Hope that makes sense. And so what happens is this person here gets ripped away by a whole bunch of waters. Make sense? Normally the minus would not be stable without the positive. Normally a minus needs a positive to be stable. Stable. So like right here, this positive and this negative are right next to each other. That's fantastic. That allows them to stay in a nice stable form. But you can't just rip away a negative. No, I mean, even think back to electrostatics. What do negatives and positives want to do with each other? They want to attract. Right? So how do you rip one away? Well, you're gonna need a lot of water. Okay. So here's another couple terms I want you guys to know. The terms are miscible and immiscible. You guys ever seen these before?
Is that like for the whole?
It has to do with dissolving again. If two things are considered miscible with each other, it means they do dissolve. Things that are immiscible do not dissolve. So, are these dissolving?
No.
Okay, so I'd say this is immiscible. Or miscible. I don't know if you actually said the C or not. Whereas these guys did dissolve, so this is miscible.
Like must.
Okay. There's a general term we use. I wrote it up here. Like dissolves like. Okay. What it means is that if you have polar molecules, it will dissolve other polar molecules. Non-polar will dissolve non-polar.
I wrote a polar.
I'll talk about that in a second. Give me one sec. Whereas polar will not dissolve non-polar. We gotta talk about what polar and non-polar is then. You guys ever heard that term before?
I've heard it like
Okay. I want to give you an example here of water. Water is HOH. H2O, that's water. And the way water works, if you've ever heard this before, is that the hydrogens right here, hydrogen is actually made up of just a single proton. And so hydrogen is actually very positive. And this has huge references to you guys in my physics class. I know not everybody is, but what happens to things that are positively charged? What happens to the negatives nearby them? They repel. And so what ends up happening is oxygen actually becomes very negatively charged. And so water is a very polar molecule. So let's say you're a water molecule. You're one of those little grade fibers. This side of the water molecule could attract Na+. Does that make sense? Because this negative part of water could try to pull away the positive Na+. What about these hydrogens right here? Who could they try to attract themselves to? Sure, chlorine minus. Yeah. You could have chlorine minuses attracted to this. So things that are polar will dissolve other polar things. Polar meaning that there's like a plus and a minus to them. Does that make sense? So,
Wait, can you go up quick?
sure. Like up here. So, general rule of thumb, if things are polar, they can dissolve other polar things. Things with positives and negatives to them can dissolve other things with positives and negatives. Because the positives can pull away the negatives, and the negatives can pull away the positives. Does that make sense? If you have a polar molecule and a non-polar molecule, though, meaning that one of the things has pluses and minuses, and the other one doesn't have pluses and minuses, it really doesn't have the ability to pull things apart. Okay. The last one, non-polar and non-polar, those can actually dissolve each other as well. I don't actually have a great reason for that right now, but non-polar things can dissolve other non-polar things. Yeah. Good example. Oil. Any sorts of oils are non-polar. We're actually going to spend a whole unit on this later. I don't know. Like say methane, CH4. Methane gas is actually non-polar. One of the reasons why is that when you draw it out, it goes like this: C to H to H to H to H. What ends up happening though is because it's symmetrical, it's very balanced. And so what ends up happening is like, it's almost like fields in physics. I know you're not in my physics class, but there's like a field that pulls in. But since all of the fields pull inwards, it kind of cancels each other out and makes a non-polar molecule. Whereas in water down here, you actually have a field going this way, and they really don't balance each other out. Did you talk about Vesper theory when you did Chem 20 before? Maybe it's been a while for you. It has to do with molecule geometry. We're going to spend a whole unit on that later, if you don't mind just waiting on that. I'm not going to test you on that just yet. So, what I do need you guys to know, though, is if I tell you a molecule is polar, it can dissolve other polar molecules. Does that make sense? So, and water, by the way, is polar. Okay, a couple other things. How do you make things dissolve faster? Like, let's say you really need to make things dissolve quickly. Well, agitation is the first term I want you to know. Do you know what agitation means, though, in a chemistry point of view? Yeah. Rub her hair, that's agitate. Agitate in chemistry means stir. Yeah. If you try to stir something, it'll dissolve faster, right? Okay, another thought here. Anybody ever go to like say, actually different example, making tea or coffee. When you want to make tea or coffee, there's two main ways you can make tea or coffee. You could put the coffee into cold water, let it brew for a little while. I don't know if it would really brew. And then you could take your coffee cup to the microwave and heat it up. That's not what we do. What we do is we heat up water really hot, and then the hot water then dissolves the coffee or the tea. Why does hot stuff work better than cold stuff?
It's moving faster.
Yes, it's moving faster. Because all things are moving. Even if you can't see them, all of this stuff here is vibrating at a molecular level. Well, the hotter something is, the more it's moving. Now let's go back to our grade 5 analogy. We've got a whole bunch of little grade 5 kids, but they're really full, and they just ate lunch, and they're not moving really fast. It's going to take them a little while to break you apart. Or we hop them all up on sugar, and now they're bouncing off the walls. They're going to move a lot faster. If they move faster, they'll break things up faster. So long story short, if you want to make things dissolve faster, increase the temperature. If you increase temperature, it dissolves faster. One more thing will affect it, surface area. The best analogy I can give for this is when you eat food. When you eat food, food eventually gets dissolved in the acid in your stomach. But it's usually best not to swallow like a big lump in your stomach. We have to chew it up first. Because it takes longer because there's less surface area otherwise. Does that make sense? So these three things will make things dissolve faster. Another definition for you then. Dissociation is a term I want to use. Dissociation describes the separation of ions. So usually we write these things as equations. Imagine you have NaCl. So NaCl is sodium chloride, basically it's salt. What happens if you put salt in water? Will it dissolve? Why? Because it's ionic. And do ionic things dissolve in water? No. Because ionic things have positives and negatives. And water is polar. And water can pull apart positive and negative things. So what's going to happen here is this sodium chloride, salt, will dissolve into Na plus and Cl minus. Now if I try to filter this stuff out, I won't be able to. Because it's not a solid anymore. It's now broken up into aqueous. We call these things ions. We've talked about those before, the idea of atoms versus ions. But the only reason these ions are stable is because of this AQ. If it wasn't for water, you couldn't break this salt apart. Let's say I threw a lump of salt against the wall. Is it dissolving? No. I mean, it might break into pieces, but individually NaCl pieces, they're still stuck together. Does that make sense? But if I put NaCl in water, it'll actually rip the salt apart. So here's some examples of what we call, sorry, go ahead.
What happens when water evaporates?
It might actually recrystallize back into the solid again. That's probably the most likely possibility. Because I mean, it would be like the 5th graders leaving. And so then the positives and negatives would then reattract to themselves and reform a solid. That's a good question. Okay, here's the first main thing that you can actually like do. Most of what I've talked about so far is mostly just like theory stuff. What we could write are are called dissociation equations. Do you guys remember like other reaction types like combustion, decomposition, single replacement? Okay. Well, this is another type of equation. Okay. Dissociation equations need to be balanced and show everything else we normally do. So let's say we took KCl and we put it in water. First question, is this thing ionic? Yep. Metal, non-metal. So it would break up into K+, but I have to write the state of matter, aqueous. Cl-, I have to write the state of matter, aqueous. Okay. Let's say I didn't write the state of matter and I wrote it just as K. Does K by itself come aqueous? K by itself would come, but that's not what we're talking about. We're not talking about solid potassium. We're talking about an ion that needs water to pull it apart. What's different about this next one? Why do I have 2s and 3s there? Because it needs to be balanced. Can I break aluminum and sulfate apart? Sure, not a problem. Water is a polar molecule. It has positive and negative halves to it. The water can pull away the positives. It can pull away the negatives, like my grade 5's example over running grade 11's. Okay, that's fully possible. You have to write the AQ afterwards, though, because it's not possible without it being aqueous. But one more thought here. There are 2 aluminums right here, so you got to put a 2 there. And there are 3 sulfates right there, so you got to put a 2 and a 3 there. Does that make sense? So one last one here. This is copper 2 nitrate. So when you break it apart, you're going to get copper 2 pluses and nitrate negatives, but you need 2 of them to make it work. It's almost like this. You have a single copper and you have 2 nitrates, and normally they'd all be stuck together as one big molecule. But then water comes and rips them apart. And so then you've got your copper, and it's surrounded by water. Water is surrounding this thing, ripping it apart. Does that make sense? Well, then these guys right here, you actually have 2 of them, and they're also surrounded by water everywhere. But it's really important to point out that there are 2 of these for every one of these. That's really important, that ratio. Does that make sense? Cool. Okay, I spent a lot of time talking about things that actually do dissolve. Ionic things dissolve, but non-ionic things almost always don't dissolve. There's a few exceptions, but most of the time it has to be ionic to dissolve. Again, one more time. Why do ionic things dissolve? Positives and negatives. Water can pull the positives and negatives apart. Does that make sense? But this thing right here, this is not ionic. This is covalent. How do I know it's covalent? They're all nonmetals, right? This has negative, negative, negative. This is covalent. Do covalent things then have the ability to break apart into positives and negatives? Okay. I have another word for those, though. We call them non-electrolytes. So again, what's an electrolyte? Well, it's something that conducts electricity. If you have positives and negatives, you can conduct electricity. But if all you have is negatives, you can't conduct electricity. So covalent things are non-electrolytes. So here's what we do in this case here. Rather than trying to break this up into like carbon plus and hydrogen plus and oxygen, well, negative, I guess. Rather than trying to break it up into pieces, if they're all nonmetals, we just leave it the exact same. So the equation is kind of silly. Solid sugar turns into aqueous sugar. Because it doesn't actually dissociate is probably the better word to use. Okay. I want to use that word better. We call them dissociate. Dissociate would mean to like break apart. Does that make sense? Okay, last thoughts here. There's one more category of things we should talk about. The unit is called solutions, acids, and bases. So we really want to focus on how acids and bases work. So you guys, we've talked about this before at some point. If something is a base has OH on the end, hydroxide. Like say NaOH, that's a base. CaOH is a base. No, CaOH isn't a base. What did I do wrong with CaOH? Ah, there we go. CaOH2. I didn't make the molecule properly. These guys, these are bases because they end in OH. Okay. Whereas HCl, that's an acid. H2SO4, that's an acid as well. Okay. What we've actually discovered is that acids are able to dissolve, actually. They're the only kind of molecular compound, at least up till now, that actually has the ability to dissolve. But we give it a different term. We call it ionization. Okay. I'm going to write an equation out for you. HCl, that's an AQ, could turn into H plus and Cl minus. Okay. But H and Cl, they're both nonmetals technically. I know one's a positive and one's a negative, but technically they're both nonmetals. And so as a quote-unquote covalent compound, I gave you a general rule that said covalent compounds shouldn't conduct. Here's an exception. Acids conduct. Why do acids conduct? Well, because they actually can become positives and negatives. But it's like one of the few exceptions. That makes sense? We have a different term for it though. Rather than calling it dissociation, we call it ionization because it makes ions. So, I'm going to write this down even. Ionic things dissociate. Molecular or covalent, whatever you want to call them. If it is an acid, we say they ionize. Nothing different actually happens. Like it looks the exact same. Something breaks up into positives and negatives, but we just give it a different name. That's all. So ionic things, we say they dissociate. And covalent things, we say they ionize. The way I try to explain it is that ionic things should turn into ions, shouldn't they? Doesn't that make sense? Ionic should turn into ions. Okay. Molecular and covalent things, they don't give and take electrons, they share electrons. So they shouldn't form ions. So therefore, if they do form ions, we say they ionize.
Where is that? What's the safe bottom?
If an acid. So I think I have some more examples here. Here's the one I just showed you. HCl is a molecular compound. Molecular things do not dissociate. But if I can break it up into H plus and Cl minus, which makes logical sense, doesn't it? Then I can argue that this thing ionizes. So this will conduct electricity. This is like an exception. There's actually another way of writing this, by the way. You could write it as HCl breaks up into H plus and Cl minus. I'm going to talk about this more later in the week, but sometimes we write it with actually like water as one of the reactants. And we write it as HCl plus water, as though water is part of the process. What it means then is we formed this really different kind of ion. We call it an H3O plus. You guys ever seen that before? Okay. It's called hydronium. And basically the way it works is that it's an H plus attached to a water. So like here's water, HOH like this. Okay. Water by itself, nice stable compound. H plus by itself, hydrogen by itself is merely a proton. Just a single proton kicking around there. Protons don't normally like to stay by themselves. You know, a proton by itself is going to want to pick up an electron, probably. That makes sense. So if we want to keep it as a proton, if it attaches itself to a water, it kind of cocoons itself in there. Like it's almost like it bunkers itself in with water, because water has a bit of a V shape to it, and the proton can kind of hide inside there. And so then we call this thing a hydronium instead, where it's almost like water, but it's water with an extra H, and therefore an extra plus. So this is another way of writing it. By the way, though, we only do this for acids. Okay. I'll show you some other examples here. If I were to write NaCl breaking up into Na plus and Cl minus, is this ionizing or dissociating? Dissociating, good. Because it's an ionic compound, so it already forms ions. Okay. It doesn't really make a lot of sense to write this then. NaCl plus water makes Na plus Cl minus and water again. That's kind of silly to do that because the water is kind of on both sides. It's kind of pointless. So we don't usually write things that way. Okay. But when we talk about acids, I'll write a different acid for you guys. Let's go with HNO3. We could write HNO3 like this. HNO3 turns into H plus and Cl minus. That's a valid way of writing it, but this is called ionization because it's forming ions from a molecular compound. General rule of thumb, it's always an acid. Okay. But there is another way of writing it. H plus by itself is a proton, and protons don't normally stick around by themselves. So the other way of writing it is HNO3, add water, and what happens is this guy right here the hydrogen kind of hides inside the water, and it becomes H, rather than 2O, it becomes H3O plus, and still chlorine minus. And so both of these are valid ways of writing ionizing, whereas this is the only way we typically write dissociation. So here's what I'm hoping you guys have picked up at the end of the class then, over the course of this hour. We've learned in the past about single replacement, double replacement, combustion, formation, decomposition. There's now two more equations I need you to know, and they're very similar. One is dissociation, where an ionic compound breaks up into two pieces, positive and negative. Okay? You have to write aqueous though, because they wouldn't break up if it wasn't for water. The other equation is ionization, which looks almost the exact same, positive and negative. The only difference is we call it ionization because as an acid, it's actually a molecular compound, and it normally shouldn't form ions because it's covalently bonded. But since it does form ions, we just call it ionization. And there's two valid ways of writing that. This first one here or the second one here. Okay. Last thought, and then I'm done. There are strong and weak types of acids. Okay. I talked about strong already before. Things that conduct really well are considered to be strong. Things that don't conduct very well are considered to be weaker. So strong and weak is actually a measure of how good things conduct. There's actually a chart in your data booklet. If you guys want to grab that real quick, I want to show you this before we go. The chart is on one of the last pages. It's on pages 8 and 9. It actually goes like vertically. You guys find this? There are 6 acids that we quantify as what we call strong, meaning that they conduct really well. And so those 6 acids are perchloric acid, hydroiodic acid, hydrobromic acid, hydrochloric acid, sulfuric acid, and nitric acid. Can you guys find those 6 at the top there? Everything that's above that hydronium ion line right there, those are considered to be the 6 strong acids, which means they conduct really well. What it means then is that they form positives and negatives a lot. Okay? All of the acids below hand, they form positives and negatives, but nowhere near as effectively. So they do conduct, but only partially. Okay? Like way at the bottom, hydrogen phosphate ion as an acid can conduct, but like really weakly, like just barely. So if I were using my little indicator thing here, it might make the line go up to 1. Whereas if I put this into like one of the strong acids, this thing would conduct it as a 10.
Wouldn't it dissolve the thing though?
What was that?
Would it dissolve the...
Well, okay, so there's a difference between strength and concentration. Concentration is about how much I use in terms of, how do I describe this? It's actually tomorrow's concept. The more sugar crystals I put inside there, the more concentrated it is. And so if I use a really concentrated solution, yeah, it might actually like cause some problems on here. But if I use like what we call like a dilute solution, it probably would be okay. Any questions? Okay, last thought, and then you guys can take off here. Here's some things I'd like you guys to take a look at, read, look over at some point. Not necessarily today, but write this down somewhere. We read through 2 sections in our book, actually. I actually covered 2 chapters. Please read them. For you guys in my physics class, I've been recommending that you read. Chemistry is going to be a lot of theory, and it's important that you kind of read up on that. I've described it to you, obviously, but you should probably read through some of this stuff too. I have a few practice questions available, and I've also got a worksheet on my website if you want to practice some of this stuff in terms of the equations. Does that make sense? To be honest though, most of this you'll have to do at your own discretion and at your own time, because most of this week I'm going to be teaching stuff. Monday, Tuesday, Wednesday, Thursday, I'm doing lessons all those days. Friday is going to be a work day though. So it's not for marks, it's not due, but for something to practice and work on. Try this when you get a moment. Other than that, I'm done, so you guys can take off.
Yeah, you didn't name that water.
Oh, if you needed the wall.
I'm gonna have to watch the end of the video. I post. Oh. Didn't mean to.